quick synopsis of the ideas we covered on Friday, October 4th. First, differentials. Given some function y equals f of x, if we find the derivative as a function of x, we can denote that as y prime, the derivative, or f prime of x, or the derivative with respect to x of function y, which we can simplify to dy over dx. So dy and dx, these are differentials. So what are differentials? Let's take a look at what they are visually. Consider some graph of y equals f of x. Consider a tangent line at some point x. We know that the tangent line has a slope that is the instantaneous slope of our green function, which we could denote f prime at x. If we move delta x to the right, then this value will be x plus delta x, and that stands for the actual change in the x value. So at that x value, the change in the y value in our green curve is from here to here. That's the actual change in the y value. From this green dot to this green dot, this green segment is the actual change in the y value. So if this distance is delta x wide, the actual change in the x value from this point to this point, and if this dimension is the actual change in the y value, then if we use our linearization, our linear model that's representing the green curve, especially near values of x. For a linear model, if we go to the right, that's going to be our differential in x, and it says only go up this high, and that's our differential in y. So the change in y according to our linear prediction is the differential y, whereas the actual change in y is delta y. Okay, if y is equal to f of x, and we take the derivative of both sides, then we'll have dy dx equals the derivative with respect to x of f, which we could say is f prime of x. And if we treat the differential ratio as actual ratio of real numbers, we can multiply both sides by dx, and that will give us a formula for the differential of y. And the formula for the differential of y is f prime of x dx. However, now let's look at the same formula derived from the geometry of what differentials really mean. Focus on this yellow right triangle and the slope of its hypotenuse. Well, the slope of the hypotenuse is the slope of this gray tangent line, which is f prime of x. But in terms of Algebra 1 material, the slope of a segment is the rise over the run. So from this green dot to the red dot, the slope of that segment is the rise, dy, over the run, dx. So let's come over here and explain this algebraically. The slope of the gray tangent line is f prime of x, but it's also the slope, it's also equal to the value of the slope of the hypotenuse, which is rise over run, dy over dx. And so if we solve for dy right here, dy is equal to f prime of x times dx, which is exactly what we had before. But this derivation shows geometrically why the differential y is equal to f prime of x dx. And that concludes this little discussion, this 4-minute discussion about what differentials are and how dy is different than delta y. For optimization problems, first clearly establish exactly what is it you want to optimize. Write an equation down for that. That will be your primary. Next, is the primary expressed in terms of one variable? If it's not, then using the context of your problem, find another equation and solve that secondary equation for a variable and substitute that into your primary. At that point, your primary will be expressed in terms of one variable. And when it is, we can find the extrema of that primary by setting its derivative equal to 0. That way you'll find critical numbers. Considering those critical numbers and any endpoint values for your input variable, figure out what the output is, and then you'll know what the maximum or minimum is. Let's do an example. These are two towers, and they're pretty tall. To stop them from falling, we're going to tie guy wires to them. This will be a wire attached to the top of this tower and then spiked into the ground, and the tower won't be able to fall to the left. And we're going to also attach a guy wire to the right tower. And we want to minimize the amount of this green guy wire that we use because it's pretty expensive. Suppose we know the heights of each tower and the distance between the towers. At this point, we can ask the question, where can we place this common spike? Because it's one spike that's going to hold both guy wires. Where can we place it so that we minimize how much wire was actually used? That's the question. Our primary function will measure the total guy wire that we used, which is going to be x plus y. So the total length of guy wire, which we can call T for total, is equal to x feet of guy wire plus y feet of guy wire. This is our primary equation. How do we know? Because we're trying to minimize the total length of guy wire used. So we're trying to minimize T. The problem is we have two different variables that T is a function of. So we want to somehow change this expression so that it only has y's or only has x's. How are we going to do that? We're going to use a secondary equation. So as I said in the last slide, you can derive your secondary equation from the context. So in this problem, there has to be some kind of secondary equation we can write. Can you think of what that might be? How about now? If you're struggling at all, notice that we haven't used 50 yet. And the question is, where are we going to place this point? Because depending on where we place it, we're going to get different lengths of x and y. So maybe we'll say this would be a units from here to here, which means this will be 50 minus a units from there to there. All right, well, now we're going to use these right triangles. Using the Pythagorean theorem, a squared plus b squared equals c squared. And for the blue triangle, same thing. The sum of the squares of the legs equals the square of the hypotenuse. All right, so our goal is to have our total length function have just one variable. How can we do that? All we need to do is solve for x. So x is equal to the square root of a squared plus 40 squared. And if we solve for y here, we just have to take the square root of both sides. Y is equal to the square root of 50 minus a squared plus 30 squared. So we can do these substitutions in for x and y because if we substitute both expressions in for x and y, everything then will be in terms of a. And so now t itself is a function of a. And t is the total length of the guy wire. And this problem asked, where can we place this pin so that we minimize the total length of guy wire? Now we just have to find the relative extrema of this equation, and we've got it. So t prime of a equals, doing some arithmetic, setting this all equal to 0. We could use our calculator, but I'm going to go ahead and finish this algebraically just for the fun of it. All right, next we'll cross multiply. Let's next square both sides. I have a feeling we're going to just use our calculator for this. It's a quartic. Let's collect all of our terms on one side. Wait a second. A to the fourth and a to the fourth cancel out. And negative 100 a to the third and negative 100 a to the third cancel out. We have ourselves a quadratic. Subtracting 3400 a squared from both sides leaves us with just 700 a squared on the right. Minus 160,000 a plus 4 million. All right. quadratic formula, here we go. But first, let's factor out 100. And so we get A is 200, or 28.571. And 200 doesn't make any sense in this context. So it must be 28.571. To prove that we have a minimum length of guy wire at the critical number of A equals 28.7571, we can use the first derivative test. What is the derivative before that critical value, and what is it after the critical value? I'm just going to plug in the value 1 here, and here I'll plug in the value 30. And it was negative in this interval, and the slope would be positive in this interval. So if it's decreasing and then increasing, we have ourselves a relative minimum. We have minimized the guy wire when we place this common spike 28.571 units to the right. And at that point, we will have used 86.023 feet of guy wire. I would like to let you know that I used my calculator to quickly evaluate T prime of 1 in this interval and T prime of 30 for this interval, so I didn't have to do a lot of work with all of this substitution and evaluation. I just put this in Y1 in my calculator, and then I used the calculator to do Y2 equals the derivative of Y1, and I just evaluated these, Y2 of 1 and Y2 of 30 to get the negative slope and the positive slope. And here I did Y1 of 28.7571. So I'm not doing all these calculations mentally or with pen and paper. I'm using the calculator to minimize my work a lot for this stuff. And I encourage you to get very familiar with your calculator as well.